So let's get some practice with the subgroup test today. We'll start with this problem. Let G be a group and let A be an element of G. Define this set, the set of all powers of A, as n ranges over the integers. This has got a name. It's called the cyclic subgroup of G generated by A being the element that we're talking about. So it's got a name that implies it's a subgroup, but we should prove it really is a subgroup. You could do it with the one-step subgroup test or the two-step subgroup test. Most people find the two-step subgroup test easier. Let's do a proof with two-step subgroup test. But I will try a proof with the one-step subgroup test as well. You don't have to use both. One or the other is good enough. First thing to do is verify that your set is non-empty, though. So the two-step subgroup is really a three-step subgroup test, with the zero step being verify the set's not empty, but that's trivial. A is an element of G. A to the first, for example, is in this set. I mean, A to any power is in this set. The fact that this is non-empty is really trivial. A is in this cyclic subgroup generated by A, for example, but so is A squared and A cubed and the inverse of A. So it's non-empty. What do you have to do after that point? You have to verify that it's closed under multiplication and under taking of inverses. There's a couple different ways you could do this. You could say, for example, to verify closure under multiplication, you could say, let's say B and C be in here. We must show B times C is in there. Introducing these new letters B and C is a little bit, well, unnecessary, because what I'm about to do is very much relate them to A, but maybe for emphasis, it's worth doing it like this. Since B and C are in there, they're in this set, what does that mean? What does it mean to be in this set? It means you're a power of A. You can say there exists integers m and n such that B equals A to the m and C equals A to the n. I think when the book proves this, the author proves this, he doesn't bother with the B and the C. Just jumping right to saying, oh, let A to the m and A to the n be arbitrary elements of this set here. And if you did it that way, that's fine. That's great. But maybe if you're feeling uncomfortable about that and you want to sort of do it in the way that makes the most sense with regard to the tests, maybe you do something like this. We must show B times C is in there. That means we must show B times C is a power of A. But it's pretty trivial. By a property of exponents, which holds in groups, whether the group is abelian or not. I mean, last time we talked about a property of exponents that only worked when the group was abelian. But what I'm about to say is true even when the group is non-abelian. You can add those exponents. A to the m times A to the n is A to the m plus n. Add the exponents. That works in any group. The property we talked about the other day that only works in abelian groups was this one. This property of exponents only works for abelian groups, not for non-abelian groups. But this one works no matter what. I'll cross that off. Just a side comment. And well, if m and n are integers, then we know m plus n is an integer. Z, the integers, is closed under addition. It is a group under addition. It's closed. We know that. since m plus n is an integer, whether m and n are both positive, both negative, or if one is positive and one is negative, it doesn't matter. So since m and n are integers, m plus n is an integer. And you could say, yes, we know Z is a group under addition. Therefore, B times C is a power of A, so it's in the set, and the set is closed under multiplication. Maybe a little overboard, saying more than I needed to. You could probably get away with saying less and still get full credit here. So maybe go ahead and emphasize it's closed under multiplication. I'll put a dot there, but I could put the word multiplication. Now let's show it's closed under taking inverses. Let B be an element of this set. We must show the inverse of B is also in the set that it's closed under taking inverses. Okay, let me just be a little bit quicker here. I'll just write implications. B being in here means there exists an m in the integers such that B is a to the m. Once again, by a property of exponents, this means the inverse of B, which would be the inverse of a to the m, you can multiply those exponents. That's a property of exponents that works in any group. To get a to the negative m, what are we trying to show? We're trying to show the inverse of B is a power of A, an integer power of A. Well, that does it. If m is an integer, negative m is an integer. M being an integer implies the opposite of m is an integer because the integers are a group under addition. This means the inverse of B is a power of A. It is in the set. Therefore, it's closed under taking inverses. And therefore, it's a subgroup of G by the two-step subgroup test. And we're done. Praise the Lord. Okay, maybe a bit of overkill, a bit more detail than perhaps it's absolutely necessary, but I think it's worth doing that. For sake of time, I think it would be best not to do a complete one-step subgroup test, but if we were to do it, what would be the key idea? The key idea would be that if we multiply B times C inverse, when B and C are in the set, that is also in the set after you show it's non-empty. And if B is a to the m and C is a to the n, that can be written like that. By a property of exponents on the right, we can multiply those exponents and get this. And by another property of exponents, we can add those exponents and get this. And if you want to write that as m minus n, that's fine. If m and n are integers, then m minus n is an integer. So yes, this is an integer power of A, and we've shown B times C inverses in there. It's a way of showing it's closed under multiplication and taking inverses all at once effectively. That's why it's called the one-step subgroup test. By the way, I hope it was clear in your mind, perhaps. It doesn't matter when you write this kind of thing, whether m and n are positive, negative, one's positive, one negative, it doesn't matter. Okay. And by the way, for example, if n, for example, is negative, then remember negative n is positive. I mean, it's notation that makes you think it's a negative number, but it's not necessarily a negative number.